All right, folks, I'm ready to get started. I thought it was. There we go. Welcome back. Welcome back to 310. This is the beginning of the fourth week, so we're moving along. Today we're going to finish off finally chapter 3, the rational consumer choice. We established the model, how it works, what equilibrium means, everything we could establish about the model to provide you the understanding of the logic of the model, the mechanics of it, how a simple case looks graphically, what equilibrium looks like graphically. And so today is just going to be the math. So in order to be able to do the math, we're going to need to use derivatives. So I'm just going to cover derivatives this one time in this class. And then from this point forward, I expect you to just be able to take derivatives. If you're rusty on taking derivatives, practice the stuff. Get better at it. If you feel like you didn't do too well in your Math 103 course, then try to do better now. Like, break out your book. If you have extra time, like, do some problems. Get better at it again. Like, again, math is not something that you are inherently good at. It's something that you become good at by spending a lot of time on it. If people are really good at math, they've been doing a lot of math throughout their lives. If you're not really good at math, you haven't done enough math in your life. You need to sit down, block everything else out, and just do a bunch of math, and you'll get better at it. That's just how it works. And if you deny that, then you'll deny yourself one of the basic skills that could really take you far in this world. So just know that. I was listening to Freakonomics. I don't know if any of you listen to the Freakonomics podcast. You can just subscribe to it on iTunes podcast. They basically cover like all sorts of weird kind of like issues related to economics. And this last one was about grit, which is like stick-with-itness, like what you need to be able to become great at something. And like there was a person, she had done a study. She was talking about how to get good at anything, there's certain components you need, but one of those is just like sitting down for endless hours, working your butt off again, until you get the things that you need to get to build up the skills you need to become great at whatever it is you dedicate yourself to. There's a lot of work being done these days to support this notion that it's within everybo's grasp to be as great as the greatest person has ever been on this planet, at least intellectually speaking. And regardless of whether or not you've been exposed to that information, you should just accept the notion because it benefits you, and then just like work to actualize it, to provide yourself the evidence you need to really support the conclusion that it is true. And even without that, you should know it's true, but you should always be working to prove it to yourself. So anyway, so that's my speech that I will give all the time in this class about, the function of your performance relative to how much time you put into this class and everything else that you take on. So just work really hard and things will work out for you. I need to move fairly quickly today because I want to move through a lot of stuff. But again, everything's being recorded. This is chapter 3. We're going to do chapter 4 on Thursday, chapter 5 next week, and then the first exam is 2 weeks from today. So keep that in mind. We're moving towards the first exam. I'll talk more about it and address questions about it next week, and we'll move forward. Are there any questions about anything else you'd like me to address? No. Those are the problems I do not want you to do. Practice problems are the ones I cover in my lectures. Yeah.
Okay, yeah, that was my question. So the only problems you really want us to like really get are the ones you go over?
Yeah.
So there's nothing like in the book you can like...
The book problems will take you down weird roads sometimes, meant to highlight strange cases that will wind up confusing people that are learning this stuff for the first time. So I'd like people to stay away from those. Just focus on what I have. As we cover more and more chapters, there's enough there that it'll be enough. And believe me, like the curves will demonstrate that it will be enough. Yeah.
So do you recommend reading the book just to supplement what the lectures are?
Yeah.
Or mainly, for the most part, just
Well,
your lectures?
that's the approach I've told you to take from the beginning. Like, my lectures are the core information resource for this course, and the book is supplemental to it. It's just meant to expand your understanding of what I present in class. I would like you to read the book, but my lectures are the main source of information that will ultimately lead to exams and whatnot in this class. Yeah. They will for the true-false area. Yeah.
Maybe a dumb question, but so you also have like
Practice.
guides.
There's a practice exam for
Yeah.
each exam. Yeah.
And those have the answer keys as well.
Yeah. Yeah. Yeah.
So pretty much from what I saw in your video, you're saying that after every chapter you have a week to take mini paper. So that must mean that say I don't do chapter 2, but then I wait till chapter 3, I can do chapter 3, and then will it just keep on going from chapter 3?
Remember, you only have to do 3.
Yeah, 3.
So you just choose the ones you want to do, and then if you miss a week because you were busy or whatever, you have a one open chapter mini paper submission option that allows you to submit a paper on any chapter we've covered at any time throughout the semester. Only one, yeah. So beyond that, you'll see due dates as we cover chapters for mini papers. Like this one today, we'll finish chapter 3, so I'll open up the mini paper. It'll be due next, I'll make it due next Wednesday or something. All right, anything else? Happy Valentine's Day. Hope you guys are able to enjoy it, but make sure that work is your priority no matter what, folks. It's going to benefit you in the long run, believe me. All right, we're going to go over derivatives, and then we'll go over some rational consumer choice practice problems, and then finally I'll go over the method of the Lagrangian multiplier that is in the appendix. It's something that I will not expect you to do in this class. It will be extra credit if you choose to apply it on the exam, but it's something that you should be exposed to, and so I'll cover it. All right, so this will be like a bare bones like introduction to derivatives. I'll go through the different cases. Basically anything that you'll need in this class, I'll go through. So just in general, the main problem of differential calculus, so calculus dealing with like changes basically, deals with finding the slope of the tangent line at a point on the curve, right? So if you have just a straight line, it's really easy to get the slope, rise over the run, slope is constant along the line, standard. But if the curve is like moving along, there's ups, there's downs, like you can't say, well, the rise over the run is this at this particular point by using your standard approach. So we use a different approach to be able to get an estimate of how the relationship is changing at every point when the curve does not have a constant slope. In high school geometry, a tangent line or tangent to a circle is defined as a line that meets the circle at exactly one point. Right, so here's the circle, there's 3 different tangent lines. The idea of a tangent is not very useful for other kinds of curves. You might have this curve here, where you have a tangent line that is just touching the curve there, but it's cutting the curve through 2 different points over here. To obtain an adequate definition of a tangent line, we use the limit concept and the geometric notion of a secant line. So I'm not going to go over limits here because it's beyond the scope of what I can cover. But it's something that you did cover in your introductory calculus courses, and it is the basis for what we do. But I will kind of generally go over how it's related to the derivative. So a secant line is a line that intersects a curve at exactly 2 or more points. So let's say we want to define a tangent line at point P. Let's say we wanted to define a tangent line at that point that tells us how this curve is behaving at that point, meaning that as x changes at that point, how much is y being affected at that point? So let's say we have this other point Q. Then if we connect those points, you've got a secant line. It's got a line cutting the curve at 2 different points. But let's say we were to have Q move closer and closer to P. So if Q moves along the curve and approaches P from the right or the left, the figure shows the typical secant line. So let's say we were to move it down, or maybe even have it on the other side and move it closer to P. Then if you connect each of those Q's with P, then you're going to have these secant lines that come closer and closer to the point that we're interested in from both sides. And eventually, the distance between P and Q will get so small that you'll have a line that's basically just touching the curve at P. So in both cases, whether it's coming from the left or the right, the secant line approaches the same limiting position, which is the line that's just touching that point P. The common limiting position of the secant line is defined to be the tangent line to a curve at some point P. This definition can be applied to curves in general. So the slope of a curve at a point P is the slope, if it exists, of the tangent line at P. So we approximate the rate of change at a point by taking the slope of the tangent line, which is the limiting position of these secant lines at that point. So consider the curve, let's say f of x equals x squared, and the slopes of some secant lines PQ, where let's say the point P is equal to 1, 1. So we're at that point 1, 1. Here's x squared. It's just kind of like that U-shaped curve. So let's say there's some point Q that happens at, in this case, 2.5, 6.25, and P is at 1, 1. Then the slope of PQ is your standard rise over run, right? So the rise in this case is 6.25 minus 1. The run is the difference between 2.5 and 1. So in this case, we simplify, we get 3.5 in this case. So that's the slope of that line, PQ. If we were to do what we did earlier and just bring Q closer and closer and then get the slope of those lines, this table kind of represents what would happen. So this is the furthest away point that gets a slope, that gets a secant line with a slope of 3.5 Gesundheit. As we get closer, we see that the slope of the line starts to converge onto 2. It goes from 3.5 to 3 to 2.5 to 2.25 to 2.1 to 2.01. So as we move Q closer and closer to P and take the slope of the lines that connect those 2 points, we see that the slopes start to converge onto 2. So the limit of the slope of the secant lines is an approximation to the rate of change of a curve at a point which we call the derivative. All right, so that's what's happening behind the scenes, right? That's what the derivative is. So once you understand what it is, then we have just some basic rules to just take the derivative of an equation, and that's what I'll cover here. Now, this doesn't require your understanding of what the derivative is, but you should always want to understand what you're doing, or else you'll have no idea what you're doing. You're just doing something that you've memorized to do versus like you truly understanding and wielding the tool the way it was intended. But in the end, as far as the purposes in this class, I just expect you to just apply the tool in the way that we're going to cover here. So we'll go through the basic derivative rules. So if you have the derivative of a constant function, a function that is not changing, so like let's say you have some number c that's constant, then this is notation for the derivative, the dc dx, the change in c with respect to the change in x would be 0 because c is constant, c is not changing, and so therefore there is no change, so the derivative is 0. So the derivative of any constant is 0. This is a constant function plotted at c, and we see that nothing is happening with respect to x. X changes and c is remaining where it is. So f of x equals c. The derivative of a constant function is 0 because the derivative tells us the rate of change of something, and if something is constant, it's not changing, so it'll always be 0. All right, so the derivative of a constant function is 0, where again d dx denotes the derivative. We can also write the we can also write the derivative of like a function f of x as f prime of x, as you know. Just some examples of some derivatives of constant functions. The derivative of some constant function where f of x equals 3 equals 0. The derivative of some constant function where g of x equals the square root of 5 is just 0. There's no variable in there, x. If you have some function, some huge number, 1,000,009 something, raised to the power of 807 something, that's just a number. It's constant. There's no variable in there. The derivative is 0. All right, so the next rule gives a formula for the derivatives of x raised to some constant power, which we call a power function. So you have x raised to some power a. So basic rule for derivatives of functions of this form, very simple. If a is any real number, then what you do is you just multiply the whole function by the exponent and then subtract 1 from the exponent, right? So that's how you take the derivative of a power function. And this is basically giving you the equation for the slope of that line at any point on a curve. So as you move along a curve and you change x, this equation will give you the slope of that line that's just tangent to the curve at every point. And there's basic properties that allow you to be able to take derivatives in such a simple way after having understood like the mechanics of the derivative via understanding limits and all that. That's stuff that you learn in your 103 class. Here I'm just going over how to take derivatives so that at least you have a reminder of how to do it for what I expect you to do. Is there a question?
Yeah, is the x coordinated with the axis? The x-axis or just x?
Well, it's the x variable, and we generally assume it to be on the x-axis, right? All right, so example, f of x equals x, right? What is this being raised to the power of? It's being raised to the power of 1, right? So you multiply x times 1, and then you're subtracting 1 from 1, right? So then you're left with x raised to the power of 0. Anything raised to the power of 0 from our properties of exponents equals 1, right? So again, you multiply this by 1, subtract 1 from the exponent, and you're left with 1 times x raised to the power of 0, which means you're left with 1 times 1, x raised to the power of 0. Anything raised to the power of 0 is equal to 1. So then you're left with f prime of x equals 1. So if you have some function that's a power function raised to the first power, the derivative of that will be equal to 1. If you have some function like this, x raised to the power of negative 10, you multiply the whole thing by negative 10, and then you subtract 1 from that. So what are you going to get? X raised to the power of negative 11, right? Negative 10 plus minus 1, which is negative 11. So you multiply the whole thing by negative 10 and then subtract 1 from that. So remember, this is stuff that if you're rusty on, you need to practice it in order to get it down. All right, so that's the derivative of x raised to negative 10. So this will tell us the slope of the line of this function at any point along it. And that slope is going to be changing because it's not a straight line. In this case, it's a power function. So the slope is going to be different at different points. So this equation will give us the ability to measure that rate of change at any given point that is changing along the line. Sometimes the function must be rewritten so that it has the proper form for the rule to be applied. So if you have some function 1 over x raised to the 10th power, this is equivalent to what? X raised to the negative 10th power from the property of exponents that we went over on Thursday. If you don't remember those, go through them, please. Like, you got to get this stuff straight because I don't want this to be the reason why you don't do well here. Like, in fact, I don't want there to be any reason why you don't do well here. I want you to do well here. So that's why I go over this at least once. Anyway, yeah, so this is 1 over x raised to some power is equivalent to x raised to the negative of that power. So you have f of x equals x raised to the negative 10th power there. If you have the square root of x, what is that equivalent to in terms of exponents? X raised to the 1/2 power. So if you have a square root that's equal, the same thing as writing x raised to the 1/2 power, and now you multiply the whole thing by 1/2, subtract 1 from the 1/2. So you have 1/2 x times x raised to the power of 1/2 minus 1, which means you're left with 1/2 x raised to the power of negative 1/2. That's the derivative of our root function. X times the square root of x, right? So you have x times x raised to the 1/2 power. So you have the same base, and that's being multiplied with different exponents. That means you add the exponents. So you have x raised to the first power and x raised to the 1/2 power. So that means this is equal to x raised to what? Right, 1.5 or 3/2, right? So you have x raised to the first power times x raised to the 1/2 power, which is equal to x raised to the 1 plus the 1/2 power, which is equal to x raised to the 3/2 or 1.5, however you want to write it. And then taking the derivative, you multiply the whole thing by 3/2, subtract 1 from the 3/2, and then you're left with 3/2 times x raised to the power of 1/2. All right, constant factor rule. So if f is a differentiable function, and c is a constant, then if you have that function times a constant, it's going to be differentiable, and essentially you just leave the constant alone and take the derivative of the function. So the derivative of a constant times a function is the constant times the derivative of the function. So you have 5x cubed. You leave the 5 alone. You multiply the whole thing by 3. You subtract 1 from the exponent. So you've got 5 times the derivative of x cubed. So I multiplied the whole thing by 3. So 3 times 5 is 15. And then you're left with x raised to the power of 3 minus 2, which is equal to 3 minus 1, which is equal to 2. So the derivative of this function is equal to 15x squared. The sum or difference rule. So let's say you have two functions that are being added or subtracted. The derivative of the sum or difference of those two functions is equal to the derivative of the first function plus or minus the derivative of the second function. The derivative of the sum or difference of two functions is the sum or difference of their derivatives. So example, you've got this function here being added to this function here. So we've got this one here. We know that's going to be equal to 15. What did I do here? Oh, yeah. So I rewrote this as x raised to the power of 1/2 or x raised to 0.5 so that I could take the derivative of it. Now I'm going to multiply this thing by 5. So I'm going to get 15x raised to the 5th power minus 1. So we have 15x to the 4th power there plus 0.5 times x raised to the power of 0.5 minus 1, which equals 0.5 times x raised to the power of negative 0.5. So the derivative of a sum is equal to the sum of the derivatives. The product rule, so when functions are being multiplied, it's slightly more complicated, as you remember. If you don't, I'll remind you. So if f and g are differentiable functions, then their product, meaning you're multiplying the functions, is also differentiable. And so the derivative of the product of these functions is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function, the product rule. Something you have to practice if you're rusty on it. All right, so the derivative of the product of two functions is the derivative of the first function times the second plus the first function times the derivative of the second. So you've got two functions here. They're being multiplied. So we're going to take the derivative of the first function, leave the second function alone. So the derivative of the first function is the derivative of a sum of two functions. So we take the derivative of each and just add them. So in this case, f of x is the first one and g of x is the second one. So the derivative of the entire product of these functions is equal to the derivative of the first function, which is 2x plus 3x. So then you've got 3 times x, right? X raised to the first power, multiply the whole thing by 1. Then you have x raised to the first power minus 1. So you have x raised to the 0 power, which is equal to 1. So you're just left with 3. So 2x plus 3 times the second function, 4x plus 5, plus the first function, x squared plus 3x, plus the derivative of the second function, which is equal to what? 4, right? The derivative of this is 4. The derivative of a constant is 0. So that's equal to 4 there. And then, of course, you just multiply things out and combine like terms. And then you get to the final answer here. My purpose here is to remind you of how to use the product rule. Yeah?
So, I mean, in other words, we could have done it, just spoil it, and then take the derivative.
That's another thing you could have done. Yeah. But I wanted to highlight the nature of applying the product rule. All right. Chain rule. And FOIL is multiplying two functions like this, right? So you do the front, the outer, FOIL, F-O. Oh, yeah, first. That's what the F stands for. Yeah. So first, so you multiply the first, and then you multiply the outer, and then you multiply the inner, and then you multiply the last, right? Anyway, all right, the chain rule. All right, so sometimes you're going to have a function within a function, and you're going to use the chain rule to differentiate. So if y is a differentiable function of some variable u, and u is a differentiable function of x, then y is a differentiable function of x. That's a little bit confusing. Let's get to actual numbers and figures here and figure out what we're talking about here. So the derivative of y with respect to x is going to equal the derivative of y with respect to u, because y is a function of u, and then u is a function of x. So in order to get the derivative of y with respect to x, You have to take the derivative of y with respect to u, and then take the derivative of u with respect to x to get that derivative. So it's applied to what are called composite functions. So you've got y equals f of u, where u itself is a function g of x. So you have f of g of x. So that's the way to write a composite function. So we can think of this function as a composition or a composite function. You've got an outer function, which is u to the 100th power, and then you've got the inner function, which is this polynomial here, so x cubed plus x squared plus 6. All right, so if we let f of u equal the outer function, which is just something raised to the 100th power, we'll call that something u raised to the 100th power. And then u is also, and u itself, the inside variable, is a function of x. So we let u equal g of x, which equals the inside function, x cubed plus x squared plus 6. Then y is going to equal the basically the composite of our f and x. So basically the outside function is f and the inside function is g of x. So to get the derivative of the entire function, we take the derivative of the outside function first. So here's a power function. You multiply the whole thing by 100, subtract 1 from the exponent. So you have 100u raised to the 99th power. That's the derivative of the outside function. And then you take the derivative of the inside function, which is a sum of these three functions. So you take the derivative of those. So you're going to have 3 times x, subtract 1 from the exponent, so 3x squared, plus 2x raised to the power 2 minus 1, so 2x, and then plus the derivative of 6, which is a constant, which is 0. So to get the derivative of a composite function, you take the derivative of the outside function, then multiply by the derivative of the inside function. So we're going to multiply these. So you've got 100u to the 99th power times 3x squared plus 2x. And then we're going to substitute back in what u is. U is the inside function here. And that will get you to the derivative. So the chain rule, not as complicated as it seems, but you just have to be careful and just keep things organized. Figure out what's the outside function, what's the inside function. Take the derivative of the outside function, multiply it by the derivative of the inside function. You take the derivative of the composite function. And finally, one derivative that you may not have taken yet, but I will teach you how to take, and that is a partial derivative. So sometimes you have a function of more than one variable, and you just want to know how is your dependent variable changing with respect to the change in just one of the variables. So remember we talked about our utility functions and how they can be a function of multiple goods, right? We've been considering a two-good world in our rational consumer choice model. So our utility is a function of two goods in our model. So then the question is, like, what is the marginal utility with respect to one good versus another? Well, you take the partial derivative of the utility function with respect to x to get the marginal utility of x, and then you take the partial derivative of the utility function with respect to y to get the partial derivative with respect to y. There's slightly different notation for a partial versus a normal derivative. Normal derivatives it would be du dx. When you're taking a partial derivative, because the function is a function of more than one variable, you use this kind of weird upside down 9 partial sign. So let's say we're looking for the partial derivative of our utility function. So the marginal utility of u with respect to x, evaluated at x equals 3 and y equals 8. So that's what we're looking for here. Basically, at the 0.38 on our indifference curve that relates to a certain level of utility, what is the extra utility you gain from consuming one additional unit of x and not consuming more additional units of y? All right. So again, there's a difference between notations there. So this is the utility of just one function of just one variable. So in that case, it would just be du dx. What's the derivative of this with respect to x? It's just 30, right? So x raised to the power of 1, multiply the whole thing, subtract 1 from that, x raised to the power of 0 equals 1, times 30, you're left with 30. Derivative of 13 is a constant, which is 0, so That's that. So du dx equals 30. All right, so let's take the partial derivative of this with respect to x. So when you're taking the partial derivative of a function with respect to a variable and there's more than one variable in there, the other variable you just treat as a constant. Imagine it's just a number and just treat it as you would any constant when you're taking a derivative, right? The derivative of a constant times a function is a function of the constant times the derivative, right? So if you're taking the derivative of this with respect to x, then you can think of it as just being the function of one variable, so one power function, so x being raised to some exponent, beta, times some constant a. And a can be everything but our variable, so 11 y to the fourth can be part of that constant. And then you've got, in this case, let's say beta is equal to 4, because that's the exponent for y there. So then you've got, did I screw up here? No, I did not screw up. Okay, I know what happened here. So a is gobbling up everything that's not x, and then we know that x is being raised to the fourth power, so that's what beta is. That's what I meant there. That's what I screwed up. Okay. Anyway, all right. So now I'm going to take the derivative of this with respect to beta. So I'm going to multiply the whole thing by beta, subtract 1 from beta, right? And we know that beta is equal to 4, and we know that a is equal to 11 4y. Everything else in the equation. So plugging that back in. 11 4y, we multiply the whole thing by 4, subtracted 1 from the exponent of x, so we're left with 4 times 11 y to the fourth times x raised to the power of 4 minus 1. So that's the only thing you do when there's an extra variable in there. You just treat it as a constant. So the partial derivative of this with respect to x is equal to, it's going to equal 44 x to the third power y to the fourth power. So here's the partial derivative of our utility function with respect to x. And then this can be evaluated at the point 38. So if we were to plug in 3 units of x and 8 units of y, then we could figure out what the marginal utility of adding 1 more unit of x would be, leaving the amount of y alone. And that would affect our total utility. In this case, plugging stuff in, we get a very large number, very large marginal utility from that extra unit of x. I'd say consume it. All right, now derivatives and math and all that, ideally out of the way. If this is review and there is a prerequisite for this course, and I hope you did well enough in it to know exactly what I just covered. Remember, not everybody's here right now, so I'm talking to everybody in the course, not just you in the class. But if you have not like mastered this stuff, you need to work on it right now, or else this whole course is going to be a disaster for you, because we're going to be taking derivatives nonstop until the end from this point. So, all right. Now, getting back to what we actually did in this chapter, right? We identified the best way to model the behavior of consumption, right? We established preferences, which were reflected in our indifference curve map, which is part of our utility function. So our utility is a function of the various goods that are consumed. We're thinking about a two-good world. People have preferences over how much of each they want to consume. And it left to, an unconstrained case, people would consume as much as they want of everything. We live in a world where there isn't enough of everything to go around, so our preferences are constrained by our budgets and the prices that we face for the goods, right? So we interacted our preferences with budget constraints to get to an optimal consumption bundle. The optimal consumption bundle represented the most preferred combination of the goods that are available that exhaust a person's income. If a person was not consuming that optimal consumption bundle, then they were at some optimal consumption bundle where the marginal utility per dollar spent was higher for one good than the other, meaning that if you had $1 and you had the option to spend it either on good X or good Y, then the extra amount of utility satisfaction you get from spending that dollar on good X would be higher than on good Y. In that case, you would consume more of X and less of Y. Because we know that the relationship between a person and what they consume exhibits diminishing marginal utility, each additional unit of a good provides them less satisfaction than the prior unit. And so if the person is out of equilibrium and their marginal utility per dollar spent is not equal, therefore they can get higher satisfaction from consuming one good than the other. As they consume that one good, their marginal utility will diminish for that good, eventually equating the marginal utility per dollar spent across all goods, getting them back to the equilibrium. That's what that equilibrium was. We went over it in fine detail last week. If you don't know what I'm talking about, go through last week's lectures again, figure it out, make sure you have it. It's a powerful model. You'll see it in finance classes, you'll see it in econ classes, you'll see it in a lot of places. So that's that. Anyway, I don't have time to go over all of it again because we already went through it an entire week's worth of lectures. Now we're just going to do some math problems reflecting how I expect you to be able to demonstrate your understanding of what we did in the model mathematically by both merging your understanding of the model with your understanding of math. All right, practice problem 3.3, utility maximization, 7 parts, optimal consumption of movies. If your weekly income is $630 and a movie show has a price of $10, how many shows can you afford per week? 63, pretty simple, right? So that represents if we have, let's say, movie shows on the x-axis. For the budget line, it represents the x-intercept for the budget line, the most movies that you would be able to afford if you only spent your income on movies. So movies are on the x-axis. We're going to assume that the other good is the composite good, which has a price of $1 by assumption. And basically it represents the leftover income after you consume the amount of the good we're considering, in this case, movies. So the most you could consume of movies is $63, which would exhaust your income, or you could not purchase any movies at all, and you would have $630. So let Y be the amount of all other goods that you spend on your money on, which is the composite good. If you plot Y on the y-axis and movie shows on the horizontal axis, what is the slope of your budget constraint? So remember, there's different ways to get the slope of the budget constraint. You can just remember that the slope of the budget constraint is the negative ratio of the price of the good on the x-axis to the price of the good on the y-axis. That's one way to do it, just by getting it out of your head. Another way is to derive it. So again, we're assuming the other good is a composite good. If you only consume the other good, which we assume to have a price of $1 always for the composite good, then you would have $630 and no movies. The value of the income that the consumer we're considering has is equal to everything that they purchase. We assume they exhaust their income, so these are going to be equivalent, meaning they spent all of their money. And so it's equal to the value of all the movie shows they purchased plus the value of their leftover composite good. Income is $630, movie shows are S, price of S is $10, Y is a composite good, price of Y is $1. So we can plug these in and we can get this expression here, and then we can solve for Y in terms of S to get our slope-intercept form of the line. And so the coefficient on the S variable here is going to be then the slope of the budget line, which is going to equal -10. Remember, the slope of the budget line represents the market rate of substitution, the opportunity cost of consuming shows. So each additional unit of a show costs you, in this case, 10 units of the composite good, which is $10, which makes sense in the framework that we're considering. But just remember that there's a lot of information in the slope of the budget line. All right, so we're looking for the slope of this line here. So one thing you could do is just remember that it is negative the ratio of the price of the good on the x-axis to the price of the good on the y-axis. The price of the good on the y-axis is $1, so it's negative the price of the good on the x-axis, which is movie shows, which is -10. So that's the answer there. Part C. Your satisfaction is measured by the utility function U of S and Y. So you have your utility, your overall satisfaction is a function of the amount of shows you consume and the amount of money you have left over. And the specification of that utility is this. So this is what that actual function looks like. So you have your movie shows raised to the power of 0.1 times the amount of money you have left over raised to the power of 0.9. This is something you would just be given in the problem. You'd be given the utility function. And again, the utility function represents the preferences of the consumer that we're modeling. It represents how subjectively they think about the goods that they're consuming. So S is the number of shows you watch, and Y is the number of other goods you use per week. How many shows should you watch on average per week to maximize your satisfaction? So the question is, like, at the optimal consumption bundle, how many shows does this person consume? That's what the problem is asking. So here is the highest indifference curve that the consumer can consume on. It's going to be the one that's just tangent, just touching our budget line. And so at that point, that's going to be the optimal consumption bundle. So at that point, there's going to be some leftover money, and there's going to be some amount of movies that are consumed that are going to be the most that this person is willing to consume, given the preferences embodied in the utility function, which is partly reflected in the indifference curves. All right, so we need to figure out what this is, what S is. That's what we need to figure out. All right, so there's a couple of ways to approach it, and now everything we've done since the end of last Thursday to today is going to come into play. All right, so we know that at the optimal consumption bundle, the slope of the indifference curve is equal to the slope of the budget line. The market rate of substitution is equal to the marginal rate of substitution. The marginal rate of substitution is the subjective rate of substitution that a person has over the goods that they can consume. Meaning, like, how much are they willing to trade off one good for another in order to remain as good off as they were before? That's the marginal rate of substitution, the slope along the indifference curve. At the optimal point of consumption, those slopes are equivalent. The slope of the budget line, the relative price of the two goods, the market rate of substitution, what the markets expect the trade-off to be versus what you want it to be, which is embodied in the indifference curves. At the optimal point of consumption, those points are equivalent. We know that the marginal rate of substitution is equal to the negative ratio of the marginal utility of the good on the x-axis to the marginal utility of the good on the y-axis. And we know that the slope of the budget line is equal to negative the ratio of the price of the good on the x-axis to the price of the good on the y-axis. We move these things around. We know that at the optimal consumption bundle, the marginal utility per dollar spent is equivalent across all goods. Again, that means that at that point of consumption, the consumer spends $1, and regardless of what they spend $1 on, they're going to be as happy across all the goods. But if they're anywhere else besides that optimal point of consumption along the budget line, then the marginal utility per dollar spent will be greater for one good than the other. And so the person will want to spend that dollar on the one that gives them the greatest amount of satisfaction, eventually moving them to this point of equilibrium. All right, so that's where we're headed. All right, to solve for this. So the first thing we want to do is we want to solve for y in terms of s in the budget constraint. So you want to get the budget constraint into that slope-intercept form that we've been doing 1,000 times. So here's that budget constraint. We figured out that the slope-intercept form is y equals 630 minus 10s. And this is a way to simplify the problem. Once you do that, then we can plug this into our utility function to simplify the utility function into a function of just one variable s. So we're going to plug this expression in for y in the utility function. So you've got utility equals s raised to the power of 0.1 times y raised to the power of 0.9. And then we plug in for y our budget constraint expression expressed as the slope-intercept form. All right. Now, we need to take the derivative of this, right? So we need to figure out the amount of movie shows that's going to maximize the marginal utility. And if you want to maximize anything, you need to take the derivative of it, set it equal to 0, and then you're going to find what the value is that's going to maximize that. If the curve is convex, it would have a minimum, and so that's what that would accomplish. But we're not looking at minimums here. Utility functions are concave, meaning they have a maximum. That's what we're looking for. We need to take the derivative of this with respect to s. All right, so you see that we have a product here of two different functions, right? One function times another function. We can't multiply it through and simplify, so we need to use our product rule. But we also have a composite function here, so it's going to make it even more complicated. All right, so we're going to take the derivative with respect to s. So let's do that. So we're going to take the derivative of the first function. Leave the second function alone, right? We'll let the first one be f of s, and then this one be g of s. And then we're going to add that to the first function times the derivative of the second function, which is a composite function, so we'll have to use the chain rule for that. All right, derivative of the first function is equal to 0.1, right, times s raised to the power of 0.1 minus 1. Sorry, I forgot I actually wrote this for you. Yeah, so we'll let this first component be the f of s, and then this one be g of s, and now we're going to use a product rule. All right, the derivative of the first function is 0.01 times s raised to the power of 0.1 minus 1, which is equal to 0.1 times s raised to the power of negative 0.9 times g of s. Actually, no, I wanted to get the derivatives first organized before I put everything together, so that's what I did here. All right, so to get g of s, we use the chain rule of differentiation. So I'm going to take the derivative of this, right? We've got an outside function, which is u raised to the power of 0.9, and then we've got an inside function, which is 630 minus 10s, right? So the derivative of the outside function times the derivative of the inside function will get us a derivative of this function here. So we'll let's say h of s equals 630 minus 10s. So g of h, so this is the outside function, equals h raised to the power of 0.9. I used h here because I didn't want to use u because we already have u for utility. All right, anyway, so the derivative of the outside function is equal to 0.9 times that term raised to the power of 0.9 minus 1. So that's going to be the outside function, so that's dg dh. That's what we got there. And then the derivative of the inside function is equal to what? Negative 10, right? 630 is a constant, that's 0. And then negative 10 times s, you have s raised to the power of 1, multiply the whole thing by 1. S raised to the power of 1 minus 1, which is equal to s raised to the power of 0, which is equal to 1. So you have negative 10. All right, so the derivative of the inside function is equal to negative 10. So then the derivative of the entire function, g of s, this one, we're getting the derivative of this function, which is a composite function, is the product of the outside function times the inside function. So you have 0.9 times h raised to the power of negative 0.1 times negative 10. That's just the product of these two. And then we'll plug back in what h is. H is 630 minus 10s. So then I multiplied negative 10 times 0.9, which is negative 9, times h raised to the power of negative 0.1, which is 630 minus 10s raised to the power of negative 0.1. All right, so now we have the second derivative we need to be able to use our product rule. In the class I taught, the professor just gave the students this question. He never showed them a thing. So it was just on the exam. There was homework problems that he never explained how to do. That's what you'll get in classes like this most of the time. And some people think that it's good. It's a good approach, a sink or swim approach. Yeah, you really get those people that are really trying, but then you lose a lot of people. So I don't like that approach. So that's why I go through these things very carefully. But in the end, like if you're not even paying attention and don't care, it's not going to go out. It's not going to work out well for you no matter what I do. But there are some marginal people that need this and are willing to try. And if they get stuff like this, then they wind up doing well. And that's why I do this. So just be okay with it overall, please. Anyway, so we're using the product rule. So we're taking the derivative of this with respect to s. So we take the derivative of the first function, which is equal to this, right? Times the second function, which is 630 minus 10s raised to the power of 0.9. So that's that. Plus the first function, s raised to the power of 0.01. Times the derivative of the second function, which is composite, which we did in the previous screen. So we get this expression here. All right. Now, having taken the derivative, we need to set the derivative equal to 0 and solve for s, which takes us back to that complicated problem that I did at the end of last class using all the property of exponents. It's going to be a similar expression now, and we need to be able to use the property of exponents to be able to solve for s when you have such a complicated expression. So this is our expression. We need to solve for s here. So remember, you've got a couple of terms here. Their exponents will add to 1 if you manipulate it the right way. And this term, same thing. So you just need to figure out what you need to do here in order to get rid of those exponents so you can combine your s's. So the first thing I did was I divided the entire problem by the first term here to be able to get rid of the exponent on just the s variable that's by itself and not within the parentheses. So the 0.1s drop out there. And these s's drop out, so we're left with 630 minus 10s raised to the power of 0.9 here. And then over here, we've got s raised to the power of 0.1 over s raised to the power of negative 0.9, which equals s raised to the power of 0.1 minus negative 0.9. So that's the power, right? So that's going to equal 1 there. Times the second term here. So I divided negative 9 by 0.1 there to get me to the negative 90. That's where that came from. And then that term is what it is. And then, of course, 0 divided by that term is 0. All right. So then we've got this term plus s, plus 90 times s. I'm sorry, not minus 90 times s, because there's a negative 90 there. So there's that. And then we've got, of course, this term in the parentheses. And now we want to get the s's out of the parentheses. So we're going to divide both sides, in this case, by this term here, raised to the 630 minus 10s raised to the power of negative 0.1. That's going to cancel out on the right. And then this will get rid of the exponent on the left here. So on the left, we're going to have 630 minus 10s raised to the power of 0.9 minus negative 0.1, right? Properties of exponents allows us to do this, to go from this to this. And then you have negative 90s because these terms cancel out. And then 0 minus that divided by that term is 0. And now we can just combine our s's. And yes, I am exhausted just describing this to you. But that's the nature of these problems. You know, they're big, but in the end, it's worth it. Yeah. You will not get multiple questions like this on the exam, but there will be multiple questions on the exam from different parts of what we covered, so you have to be ready to do anything. All right, so 630 minus 100s equals 0. Get the 100s on the right there, so you have 630 equals 100s. Divide both sides by 100, and that gets us to 6.3 shows. 6.3 shows is the amount of shows this person will consume to make them the happiest possible given their preferences and the prices they face in the market. Hey, it is what it is. All right, so remember, like, this is about taking your understanding further than where it already was. It's easy to represent these things graphically, but graphical representations are limiting in the sense that they don't allow you to go to the more complicated cases. You need to jump forward your understanding to the math in order to then apply it to the real world, because the real world is not made up of two goods. And you can't just use a composite good all the time. You need to be able to include all goods in there. And to do that, you need math. And so this is how you get to that point. By understanding these problems, it allows you to understand the math better, which then allows you to get to the more complicated applications, which are the ones that are actually effective. So remember, some of you are not going to go beyond this, and you're going to take this class and you may never see this again. You'll see some aspects of it, but never again. But there are people in this class that will use this as a stepping stone to go forward, and it needs to be covered in this way, or else there's a disservice being done to them. So anyway, all right. So how many shows should you watch on average per week to maximize your satisfaction? 6.3 is correct. Good job. So that's what we figured out. We figured out that 6.3 shows will be part of the optimal consumption bundle for this consumer, given her preferences described by her utility function and the prices and budget that she has. How many units of the other good do you consume? Well, you have one value, and you can get the other value in a couple of different ways. One way is just from your budget constraint, right? It relates both variables. So here's our budget constraint. If you plug in 6.3, that'll get you essentially, in this case, because we're talking about the composite good, essentially how much money do you have left over, right? In this case, it's 567. So that optimal consumption bundle is made up of $567 and 6.3 movie shows. That's the consumption bundle in this limited world in which only shows and money exists that will make the consumer the happiest possible. She's consuming at the highest possible indifference curve and exhausting all her income. So she's consuming on her budget constraint, just touching the highest indifference curve. And at that optimal consumption bundle, the marginal rate of substitution is equal to the slope of the budget line, which means that the marginal utility per dollar spent is equal across all goods. Part E, at your optimal point of movie watching, how many additional units of the composite good would you need to be as well off as before if you watched one less show a week? Do not calculate utility. So you're at the optimal point of movie watching. It's asking how many additional units of the composite good would you need to be as well off as before if you watched one less show a week. So basically, how much of that composite good do you need in order to maintain the same level of utility, meaning you stay on that indifference curve? So at the optimal bundle, we know the marginal rate of substitution, the slope of the indifference curve, is the same as the slope of the budget constraint, which we calculated to be -10. Therefore, if we watch one less show, we need to consume 10 additional units of the composite good to be as well off as before. That's what the marginal rate of substitution tells us. And so you need to answer that question, you just need to remember, okay, at the optimal point of consumption, we know that the marginal rate of substitution is equal to the slope of the budget line. We know what the slope of the budget line is. So therefore, this is telling me that each additional, giving up one movie would get me would require 10 units of money for me to be as happy as I was before. So that I would be indifferent between those two consumption bundles, which is what you need to be along the same indifference curve. So essentially, going from there to maintain the same level of satisfaction, you're on the same indifference curve. Alternatively, one could calculate the utility at the optimal consumption bundle, meaning you plug in 6.3 and then whatever the other number was of money into our utility function, get the level of utility, and then reduce our shows by 1 and find the number of Y units that gives the same utility as before. So essentially, plugging in 6.3 and 567 gets you to 361.54 utils. That's the amount of satisfaction you gain from your optimal consumption bundle. And if you decrease your movie shows by 5.3, how do you maintain your level at that same amount of utility? Well, you have to solve for Y to get that. So that's another way you could do it. Remember, if you were anywhere else besides that indifference curve, your level of satisfaction would be either higher for all consumption bundles on indifference curves above that optimal consumption bundle, which are not affordable, or it would be a lower level of utility that would wind up getting you to a consumption bundle that is not the best you could do, right? You're not using all of your money. You could do better. You could be happier. So to maintain the same level of utility, that means you have to move along your indifference curve. That means you just have to think about what is my marginal rate of substitution, the rate at which I'm willing to exchange one good for another in order to maintain my overall level of satisfaction. What is your marginal utility of shows at the optimal consumption bundle? So we know that to get the optimal number, we had to set our marginal utility equal to 0. So therefore, we know that the marginal utility of shows at the optimal number is equal to 0. So unsurprisingly, the marginal utility of shows is 0 at the optimal bundle, since we found the optimal bundle by setting marginal utility equal to 0. All right, last part. What is the actual change in utility due to watching one less show than the optimal number and holding spending on all other goods constant? Use the right sign. So this is saying you are just dropping one show from that optimal consumption bundle. So where is that landing you as far as your overall utility now? So now you just basically have to plug in the amount of the composite good that you figured out, 567, and then drop that 6.3 by 1 to figure out what your utility is for that consumption bundle. So this is the optimal consumption bundle. We know it's 361.54. If we drop our amount of shows by 1 unit, the question is asking us what is our overall utility from that consumption bundle, and it's going to be less. In this case, it's 355.3. So it gets you on a lower indifference curve. So the math expects you to understand the model, which is why you really have to understand the model in order to be able to do the problems. And then once you understand how to do the problems, then you truly understand the model. So we were here and we just lowered it by 1 unit, so we would be on that lower indifference curve there, which is 355.2, which is what the level of utility is for all consumption bundles along that indifference curve. All right, the change in utility in this case is equal to negative 6.2 utils. That's what it's asking. What's the actual change in utility due to watching one less show? So we had to get the utility from our original consumption bundle, the new consumption bundle, and then get the difference to get us to 6.2 utils. All right, let's do another one. 3.4, rational consumer choice, video games versus everything else. Jim likes to play video games online. He has the utility function v squared y. So his utility is a function of v, which is hours of playing online games per month, and y is his consumption of all other goods. His monthly income is $1,000, and an hour of gameplay costs $2 in implicit costs. So what is his budget constraint solve for y? So again, you just think about all the information you've been given. You just kind of organize what you have and then kind of throw it into the expression for the budget constraint that you understand. So you've got your expression of the budget constraint. We've got income to be $1,000. We've got V is gaming hours per month. So that's the good that he consumes, gaming hours per month. The price of V is $2. Y is the composite good. We know that because it says Y is his consumption of all other goods. So we know that's the composite good. We know the price of the composite good is equal to $1. So plugging all that in and then getting it into slope-intercept form, we get the constraint, our budget constraint solved for Y there. How many hours should he play per month? All right, so now let's go through the steps one more time. We're going to plug in our budget constraint into our utility function. So solve for y in terms of v in the budget constraint. We did that. We're going to plug this in for y in the utility function. So there's a utility function plugging in 100 minus 2v. So we see there's no exponent on this term here. So we can combine these terms. So we don't have to do all the math we did for that last problem. We don't have to take the product rule and the composite function rule and then use all the properties of exponents. This is a simpler version of the problem. So taking the derivative with respect to v, we can do it a couple of ways. We can combine it or we can do the product rule, but I combined it to simplify it. So we have a 1,000 v squared minus 2v cubed. And now I'm going to take the derivative. So we've got 2,000 v minus 6v squared. Set that equal to 0 and solve for v. So I just move that term to the right. I'm going to divide both sides by v there. Got rid of the square there, got rid of this v, and now divide both sides by 6. And the optimal amount of hours of gameplay for this person, given their preferences embodied by the utility function and the prices they face, is 333 hours, 0.33. You need to solve the budget constraint based on the information you're given. So that's how many hours should he spend on the other good each month. You plug that into your budget constraint, and in this case it's 333. So remember, I'm going to go through this quickly because these are practice problems. This is what I meant by you have to practice the problems. It's going to get bigger, more. There's going to be more of this stuff as time goes by. It becomes a bigger responsibility. All right, and finally, we can approach these problems in a slightly different way, and it might be worth your time. If you approach it in this way, like if we approach the first problem in this way, you avoid a lot of the math, but you have to understand this method, and it's its own sort of challenge. So another method of approaching the constrained utility maximization problem is to use the method of Lagrangian multipliers. The first step is to transform the constrained maximization problem into an unconstrained maximization problem via what's called the Lagrangian expression. So basically, you maximize, and this kind of weird L represents the Lagrangian expression. You maximize this expression, which equals your utility function minus this lambda here, which is called the Lagrangian multiplier, times the constraint, where you have the bigger number, which would normally be your income, being subtracted from the smaller number, which would be what you're spending. In this case, we assume they're equal, but in general, your income will be the largest number, or at least equivalent to this number. So you always subtract what would be the largest number. So if you have a budget constraint, M equals this, you put this equal, you have what your income is worth minus your income M. I have to explain that because the Lagrangian can be applied to a lot of different cases, but you won't need to apply it to any other case beyond this one in this course, but people will be moving forward. Anyway, let's keep going. All right, so lambda is called the Lagrangian multiplier. Its role is to assure that the budget constraint is satisfied. So even though the problem becomes an unconstrained problem, it is taken into consideration, the constraint, via this term here. So the first order conditions, which are the first derivatives of this expression, must be taken for x, y, and lambda. So we have to take partial derivatives of this expression with respect to each of these three variables that we're dealing with. Lambda is now a variable as well. It is not a constant. So the partial with respect to x is going to equal the partial with respect to u. So the marginal utility of u with respect to x minus, so there's only one term here with x in it, so minus pxx. So the derivative of this with respect to x is going to equal what? So you have negative lambda pxx. It's not 0. This is a number, and this is a constant too when we're taking the partial with respect to x. Negative lambda, and what else? And px as well. This is also a number, right? So this is the variable, and this is a constant, right? So you take the derivative of this with respect to x, so then it's going to be negative lambda px. So that's just kind of like the coefficient of x. Set that equal to 0. That's our first order condition. The second one is the partial of this Lagrangian multiplier expression with respect to y. So you've got the derivative of this with respect to y, which is the marginal utility of u with respect to y, partial u over partial y, minus the only term here with y is going to be negative lambda py y. So the derivative of that is going to equal what? Negative lambda py. Negative lambda py, set that equal to 0. That's our second first order condition. Then the third one is the partial with respect to lambda. So you take the derivative of this with respect to lambda, what are you going to get? Not 0, not 1. Negative the whole budget constraint, because this is essentially the coefficient on lambda. So it's going to equal this expression here. So negative, so I multiply the whole thing by the negative, and then we got our budget constraint. So this first order condition satisfies our need to constrain the problem, having made the problem into an unconstrained problem. We're going to set that, remember this method is going to be extra credit. But if you get it, you'll get some extra points. All right, anyway, so then so that's the third one there. So 3 guarantees that the budget constraint is satisfied. The next step is to solve these equations for x and y. So you've got those 3 first order expressions. The optimal x and y values can be obtained by dividing expressions 1 and 2. So this first order condition we can solve for our marginal utility of x by setting this by taking this to the right. So adding this to both sides. So you have d partial u over partial x equals lambda px. And then we can do the same thing over here. So partial u over partial y equals lambda py by moving this term to the right. So now I'm dividing that first equation by the second one. So essentially we have a ratio of the marginal utility of x and marginal utility of y equals the ratio of the price of x to the price of y, which may or may not look familiar to you. It is the representation of that optimal consumption bundle, right? So essentially we're using our optimality condition where marginal rate of substitution equals the slope of the budget constraint to solve for our x and y. And that tells us that the marginal utility per dollar spent is going to be equivalent across both goods at that optimal point. So this will help you to solve for those optimal values that we were looking for. So I'll just do a quick demonstration of just this one. Let's do this one. I might have enough time to go through both of them. I'll go through it really quickly. If you're interested in learning it, just go back and kind of figure it out. But I'll go through it really fast right now at 4 minutes. All right. Let's say income is $40. Price of X is $4. Price of Y is $2. So this is our Lagrangian expression. So X and Y is our utility function. And then we have minus lambda times our budget constraint. So we have to plug all this stuff into our budget constraint, which looks like this. So the value of everything we can buy minus our income. Now we take the partial with respect to X. Derivative of this with respect to x is just y. And then we have minus lambda 4x. The derivative of this with respect to x is negative 4 lambda. Set that equal to 0. Partial, and then we can just move that to the right. So you have y equals lambda 4. Partial of this with respect to y. So you've got the derivative of this with respect to y, which is x. The derivative of the term with respect to y in here, which is negative lambda 2y. So you have negative lambda 2. Set that equal to 0. Move this to the right, set x equal to lambda 2. And then, of course, we take the derivative with respect to lambda, which is our budget constraint there. Set that equal to 0. All right. Then we take the ratio of 4 and 5 here. And so you have y over x equals, the lambdas drop out, so you have y over x equals 2. So now you have y equals 2x. So now you have one expression relating x and y, and then you have another one relating x and y in your budget constraint. And so now you just have a system of equations that you can use to solve for your two variables. Setting y equal to 2x in your budget constraint gets you to 4x plus 8x equals 40. Divide both sides by 8, and you get the optimal amount to be 5. And then you plug that into either of your two equations that have both your variables in there to solve for y. Y equals 2x, so y equals 2 times 5, which is equal to 10. I still have 2 minutes. All right, so 510 is the utility maximizing bundle. Let's just use this method for that last problem I did, video games versus everything else. Again, monthly income is 1,000. Everything's the same as the problem was. That's our budget constraint. How many hours should he play per month? Let's set up the Lagrangian. Utility function is equal to v squared y minus lambda times the budget constraint. So the value of everything you can buy minus your money, that's there. Take the partial with respect to v, the amount of gameplay hours. So you've got 2vy minus lambda 2 equals 0. 2vy equals lambda 2. The partial with respect to y is equal to v squared minus lambda. Set that equal to 0. V squared equals lambda. And then the derivative with respect to lambda is the budget constraint. Make sure you get the negative in there. Set that equal to 0. Anyway, no, yeah, sure, whatever. All right, now take the ratio of 7 and 8 here, and then that allows you to get rid of the lambdas, and then it allows you to get another expression relating v and y. So you get, in this case, y equals v. And therefore, now you have two expressions with two variables, which you solve using system of equations, and then you can solve for your optimal amounts. All right, folks, congratulations, you made it through this. I'm going to open up the homework for this, open up the mini paper for this. I'll make it due next Wednesday for that. The homework will be due Sunday, but the mini paper will be due next Wednesday. And then beyond that, we're ready to move forward. So spend some time on this stuff. Again, now you know why my online homework assignments aren't that complicated, because you need to practice this stuff. So make sure you do. That's why they're called practice problems. Have a great Valentine's Day. I'll see you on Thursday.